So paneling, this is what the problem is. Given is a design surface, even a very complicated one maybe, and we would like to break it up into panels and see whether we can use as simple as possible panels while still be able to not far deviate from the original design intent. So this is a problem which is not completely solved. The solution which I tell you today is probably still the state of the art. Also, it was done in 2010, so it's a bit old. What we did at that time, you do a layout of these panel seams by any software you like. So this is, for example, you can put some quad mesh. Here we assume this is the case. And there is software which pulls out such quad meshes. Of course, the quads will not be planar originally. It will be very hard to make them planar, maybe. And moreover, as you have seen in this project on the Eiffel Tower, the architects sometimes don't like only flat panels. Also, this is a mathematically interesting thing. It may look too faceted, and so you will have to go to other panels as well. So we assume here that we have a design surface and the panelization seams, so these panels are more or less determined. So they are predetermined. But of course we must allow some deviation so that the entire thing can be built at a reasonable cost. Because if we just take the seams and the surfaces, surface patches of the design surface, then it will be impossible to afford the building simply because the manufacturing of such a panel may be too expensive. In general, it will be, as we say, double curved, so not developable and curved, so both directions curved, both principal curvatures not zero. So this will, in most cases, require the making of a mold, and the making of a mold is typically more expensive than the actual production of the panel using this mold. So this is out of the game somehow. You cannot do it. So what can we do? And now, the main idea of the solution is the following. I give several types of panels. So the cheapest are, of course, the planes. Then I give you, we prescribe other panels that are maybe cheap to produce. For example, here a cylinder. Remember, I told you for glass, a cylinder is still a reasonable shape. There are machines to produce curved glass in the shape of a cylinder. Then we do have here a paraboloid. Paraboloid usually, I did not tell you, but it has congruent profiles on it, and so it is a little simpler maybe to build a mold. And a hyperbolic paraboloid is even ruled. So I think it depends on the type of material you are going to use, which panel types one will actually put into the system. The system itself, the algorithm, could work with various types of panels. Yeah? So here I have the following types, plane, and you see on this design surface, for sure in these relatively flat areas, you got a lot of flat panels. And then there are some cylindrical panels, and you see here in these more feature-like areas, you have these cylindrical panels. Feature, I mean areas where you have in one direction close to zero principal curvature, in the other direction higher principal curvature, and this is natural to use here cylinders. And then you have some nasty cases, and the most nasty case is actually here the cubic. The cubic just means you have like a cubic Bezier patch or so. So a more complicated patch, which definitely would require the making of a mold. But if they are rare, these cubic patches, say it is still feasible. So, example types, as I said, the plane, the cylinder, maybe translational, rotational, depends. Yeah? And of course, a cost is always attached to each panel. So this can go into the system. And now, one can do the following. One can come up with an algorithm, and this has been published at SIGGRAPH 2010, and the lead author is Michael Eigensatz. Maybe I write this down. Eigensatz. This was published at SIGGRAPH et al., so other authors, including myself and others. SIGGRAPH 2010. And there we have an optimization, an algorithm that allows you to switch between a less smooth realization, so say with stronger kink angles, but a low cost, and let's say a very smooth, which has, of course, higher cost. It is clear that the higher quality has higher cost, so this is obvious. Unfortunately, one can hardly see this. This is actually not a very nice panelization. It is a very strange building in my home country. It is in Graz. So Graz is the second largest city in Austria. And this is a work by Cook and Fournier. And you see here this paneling. Well, it's not really beautiful. And if you go look closer, you see all the defects. You see these gaps. You see these kinks. Look at this. So this is all kinds of defects show up here. Yeah? So this is a paneling. Gaps and kink angles. So gap means the offset along the edges where they should join, and the kink means the deviation in the surface normals. Yeah, here. This is the kink, and the gap would be here between these two patches. Now, we even included the following, namely, it may be beneficial if one can deviate a bit from the design surface. So we will not necessarily stick with the given design surface. So we would allow some deviation. You may have a tolerance, say 30 centimeters for a large building may not be much, yeah, but still it may help you quite a bit. And then, this is more interesting, we were thinking here about mold reuse. This does not mean, this means the following. Yeah? I have a mold, let's assume that I have to produce a torus patch, rotational torus patch. And then I produce a mold to manufacture this patch. And certainly, I may produce different patches with the same mold, but just putting some material in a different way onto the mold, like glass, you have to heat it up, put it onto the mold, or cut the boundary out in a different way, like here. So with the same mold, you may reuse it for different panels, and this mold reuse was incorporated in this optimization. And here is an example which illustrates the cost benefits when this thing is applied. So here we have a huge amount of molds. It is a very high quality. It has no kinks, but it has 7,265 molds. This is useless. And here we have 1,501 molds and 1 degree kink. 3 degree kink, you go down to 800 molds, and so on. So here you have already 88% cost saving. So the saving is 88% compared to here. So see, it is infeasible. And the more kinks, of course, you allow, the more feasible it gets. But please note, also, I will not tell you probably the details of this algorithm because this is an entire lecture, yeah, and then I cannot talk about the other optimization. Please note, that what did I want to say? I forgot it. See, I start to become really tired. Anyway, let us look at the result. So we have the original CAD model. We have this panelization by an architect. Then we have, this I wanted to say, global. So it is not enough to locally, you have these seams, This defines roughly the location of a patch. And then I could do, let's say, the best approximation by a cylinder. Because if I like a cylindrical patch. This is not what we are doing. We put it into a global optimization, and the patch type is also unknown. And this is why it is a nasty problem, because we have, say, 5 or 6 patch types. This is a discrete variable from 1 to 5. And we need to select from this discrete variable. And then we have these continuous variables which defines your actual location of a plane, the parameters of a cylinder, and so on. So this is an optimization problem which is discrete in some variables and continuous in the other variables. And this is always painful. Yeah? So yeah, it is, of course, not possible to come up with a precise solution. You can only have some heuristics. One can actually prove here that you need heuristics, and we apply certain heuristics in this global shape optimization, and then you have a final result. And what I can really demonstrate here are some real projects, but this software just for just to demonstrate the effectivity, it has not been applied to these projects to my knowledge. Yeah? So if we do this design from glass, we have to assign certain reasonable cost values. So the optimization also takes into account the cost of a production, yeah, of the mold and of the panel. And of course, overall, you would like to come down with the cost. Yeah? The cost has to be reasonably estimated. So here, if you build it by glass, you see here the values, and from concrete, you see some other values of cost assignment, and you see, unfortunately, I do not see here how much we save, but you can read it in this paper. So this is a figure which is unfortunately not complete here. You can also do the following. This was a follow-up work, and I think it makes sense, because you can say, if I have a huge building, there will be parts of this skin which you will hardly see from any viewpoint. Because either it is very far away, or it is hidden by another building. So you could also take this visibility into account and allow a lower quality in the areas which are hardly visible. And this, of course, brings down the cost as well. So here, if you say this is this building, and people usually go on these parts, and on the other side, which nobody will see or rarely will see, you have much higher kink angles. So this shows the kink angles. It's not the cost, the kink angle. So the quality here is higher because this is more visible, and the quality here is lower. This can also be done in this algorithm. Maybe this we do not need. And now I go to what I really promised for this part of the lecture, namely to the optimization. And where is it? Here. So this is an optimization method which we call a guided projection onto constraint variety. Sounds very bad for the architects, but it is not so bad. Yeah? So usually one has to ask certain questions when you design something. And not only is it nice, but also does it work? So would it stand in architecture? And how to produce it? And of course the architects know this famous guy Antoni Gaudi. And he came up with the idea to first come up with a physical model. And since building a model which is based on compression is not so easy, he turned it around and say, I designed one based on tension. So he had these famous hanging models. And if you take this hanging model around, if it is force balance, you know, with tensile forces in the first place, if I turn it around, it is in force balance with compressive forces after turning it around. And this was somehow the basics of his designs, like this famous Sagrada Familia, which is a very complicated, geometrically very complicated design in Spain, of course, and is still, as far as I know, not really completed. So they are still working on it. And then there is, of course, other work I have already talked about, like these pavilions on the Eiffel Tower. So several parts come into play. I would say some small, simple version of physics, some kind of art is involved, and geometry. And what we would really like to do here is computational design, which takes these things into account, namely functionality, aesthetics, and whether we can actually manufacture it. So this method of guided projection is to access these design spaces. And it is called guided because we have to look at various types of aesthetics here. And I will only talk maybe about the first part, and then, because yesterday, about this form finding, and yesterday we had already developable surfaces we don't need today. And only if I have enough time, I can also show you something about these other types of regularity and patterns on surfaces. I had this transparency already up. We look at first place, but it's only for a motivation, at self-supporting structures. And mathematically, how do we express it? Let me repeat. I had it in my first lecture. A structure is self-supporting if I can put a network of forces inside, a mesh of forces inside the hull. So it must be within these bricks in the previous case. And along each edge you have acting forces. They have to be compressive. So this is an edge vector. Eij is the vector from vertex Vi to vertex Vj. And this Wij is the force density. And so this is the force acting in an edge. And along each vertex Vi, all incoming edges have to balance the weight, which is usually vertical, because we only consider here the self-weight. I'm often asked, so if you only consider the self-weight, what happens if you put a little more weight on the structure? If there is some snowfall in my country or some sandstorm here, something like this. Yeah, so what happens? It does not mean that the structure would fall down, because if you have inside your structure such a so-called thrust network, which is in balance with the dominating load, namely the self-weight, you can still put on material and would still find a thrust network that verifies that this structure stands, but up to a certain limit. When this load gets too big, there will be no thrust work inside the hull, and then it will fall down. And of course, if it depends where we place these forces in a general masonry structure like I had it before, these edges just need to be inside the masonry. There is no preferred directions. If we have a steel glass structure and we do not want to have any forces in the glass, we must have our thrust network within the steel beams, obviously. So then we are more restricted. On the other hand, if we have a steel glass structure, we can still work with this force equilibrium, but we do not really need only compression, because the steel you also can apply some tension, of course. Yeah? So this is something which you can design with it. I skip that. So what we really want to do mathematically, I have to given you in this series of talks many different constraints which were applied to these architectural structures. One was the planarity of a face. We had this cone condition, the circular condition, and so on. Now, on the previous slide, we had this force balance condition. So we had numerous conditions around. These are constraints which limit the possible realizations. So mathematically, we could say, if we have an initial design which does not yet fulfill the constraints, then we have a point outside a so-called constraint variety. And I will tell you in a moment what this means. And we have to project our point onto the constraint variety, which means our original design does not satisfy the constraints, and we have to find a design which is hopefully close to our original design and satisfies the constraints. So we can think of it as follows. Let us think we just talk about meshes for a moment. Then the unknowns of a mesh are the locations of the vertices. Yeah? Each vertex of this mesh has 3 coordinates. So in fact, if these are n vertices, we have 3n unknowns, right? This is clear. So a mesh is then a point in a space Rd, d equals 3n. If we have some fixed points, then it's a little less because, this is not unknown anymore. Now, an individual constraint can be expressed usually with help of these vertices, and then it is typically an equation, maybe an inequality, but so far we just talk about equations. It is an equation in the unknowns, and if you have one equation in the unknowns in whatever space, it limits in general your solution space by one dimension. I'll give you an example. If you are in the plane and you have one equation, for example, x squared plus y squared equals 1. This is a constraint, and it limits the entire plane to, in this case, a circle of radius 1. X squared plus y squared equals 1, right? So one equation in the plane is a curve. One equation in 3 dimensions is a surface. You know, even if in the space in x, y, z, if you write x squared plus y squared equals 1, it is not a circle, it is a surface. Is this clear? It is a cylinder parallel to the z-axis, and the base is a circle. Yeah? So one equation is a surface. And in higher dimension, one equation gives us something what we call a hypersurface. It is of dimension n minus 1. And then if we have then m such constraints, the dimension of these points in this space Rd, which satisfy all these constraints, is a so-called variety. In general, of dimension d minus m, there could be dependent constraints, and then it is not true. All kinds of nasty things can happen. Also something one should note that when I write here codimension, I mean the dimension of the normal space. Yeah? This is not necessarily 1. But this you see already in 3D. Now let us discuss 3 dimensions. If you have a curve in 3D, you need 2 equations to satisfy this curve. Yeah? You can take one function, f of x, y, z equals 0, and another function, g of x, y, z equals 0. These are 2 surfaces, and the intersection curve is the curve. And the curve does not have a unique normal in a point, it has an entire normal plane. And in general, in a high-dimensional space, if we have m hypersurfaces, we get an d minus m dimensional tangent space of such a variety and an m dimensional normal space. So this is a generalization. Now, this fast projection onto constraint varieties, I roughly already indicated in my first lectures. And the key is that we introduce new variables. If necessary, if a constraint is already nice, we don't have to do it, but otherwise we should introduce new variables so that the constraints are at most quadratic. This means linear or quadratic. These are the good constraints. And then we need to see how we solve this whole thing, and this we'll do later. So, a reminder, this I had already on the board. Planarity of a face, it needs not be a quad. Here it is a quad with vertices v1, 2, 3, and 4. Planarity means that the edges are orthogonal to a normal n, which is an unknown. So here we introduce the normal as an unknown, and just write that edges here are orthogonal to the normal. Whether it's a quad or a hexagon, we don't care. For a hexagon, we do the same. We just have more equations, right? More constraints. Hey, and another thing which is important, in some numerical optimization techniques subject to constraints, it is bad if you have constraints which are dependent. But here it does not matter. For the quad, if we just require that 3 edges are orthogonal to this normal, right angle with the normal, the 4th edge, of course, automatically is orthogonal. However, we do not want to leave out this one constraint for various reasons. And one main reason is a nightmare to code it up. because you have to make sure that in every phase you leave out one edge. That would be a nightmare. So we take all four, also for symmetry reasons. We have dependent constraints, but you will see later it doesn't matter. So this is a big advantage of the approach, which I will tell you. Or if we have to express the circularity of a quad, I do not recommend the angle condition. To this angle condition, sum of opposite angles equals 180 degrees, of course true, but how do you express this angle? Yeah? Cosine alpha equals and so on. This is very nasty because you have a trigonometric function in it. This is not a quadratic function, so you avoid it. It's much better to introduce the center of the circle as an additional unknown and just require equal distances of this vertex to the center, which is quadratic. You can simplify, of course, but I don't want to do it now. This is an important thing. We need to be close to the reference surface. So during our optimization, what we will do? We will have an initial design, and then we will change our design so that we satisfy the constraints. But we assume in many cases that we have given a design surface. So the architect has provided a design surface, and the mathematician has to compute the rationalization, right? So we have to stay close to the design surface. And this is done as follows. Assume that we have our current location of the vertex VI, is not this one, is somewhere. Yeah? Then we compute, maybe I draw it also here, the closest point. So, during this iteration, this algorithm, we will have a vertex originally in this position, and during the optimization it will change. Typically the changes will get smaller and smaller, and then at some point we will have converged to reached a solution. And so if we have the vertex VI in its current position, C means the current position, and we have here our reference surface, we compute the closest point, VI star, on the surface to this point VI. So how do you do it? If you have a curve in the plane, yeah, and you have a point, where's the closest point? The closest point is clearly on a normal. But there may be other normals here. But what you really need is a very good algorithm for computing the closest point, because this has to be computed many times. This is more or less a computational geometry problem, not really, but definitely a geometric data structure problem, because you will have to properly rearrange somehow your you have to find a good data structure, KD tree or something like this, which allows you to quickly compute this closest point. Typically you have, yeah, and you will benefit from the fact that during this optimization, these points will not make big changes, and then computing the next closest point is even simpler, because you can use this as a starting guess for some kind of Newton iteration, which is very fast. So, but this closest point computation really is a bottleneck in the speed. So most algorithms which have this closest point computation, this is a bottleneck in the time. So to VIC, to the current point VI, we compute the closest point VI star. Here we have a tangent plane in 3D if it is a surface. And then we make sure that the new location of VI, let's say here VI, is close to this tangent plane. So what do? We just say the new point VI minus VI star times Ni star ideally should be 0. So this is a constraint. Actually, one should just write Vi minus Vi star times Ni star equals 0. The Ni star is known. Why is it known? Well, because we said we make this closest point projection. So this is actually in this direction. We have Ni star. Ni star must be the vector Vi current minus Vi star normalized, divided by the norm of Vi current minus Vi star. So this is the normal. Yeah? The closest distance occurs at the normal. This is known, but in the next iteration, this is the new position of the vertex. It just says in the new iteration we want to have this point VI in this tangent plane. It may appear to you as not good. You may think it is much better to keep this point as close as possible to this closest point. And I see many publications which use it, but I think it is bad for the following. I would have more mathematical explanation, but intuitively it is bad for the following reason. If you have a design surface and you would like to achieve a design location of vertices which stay close to the design surface, you must allow your vertices to move along the surface. And if you always make your points close to the closest previous point, you somehow stick to the surface too much. And this tangent plane allows you the gliding. This, I think, is quite obvious. Because here we could even go far away. Yeah? This will be punished by another term, but we can really allow the gliding. So please note if you implement something to make sure that this closest point is not used directly, but the tangent plane is used. Now, I explain you force balance. How would we express this? Yeah, the resultant force at the vertex equals basically the sum. Yeah, it's the load. And the load can come from adjacent beams or from neighboring faces. In order to determine the weight, here we need the length of a beam, and here for the face we need the area of a face. But both the length of a beam and the area of a face can be computed with quadratic expressions. So we are also here within quadratic expressions, and the left-hand side is beautiful anyway because we have these unknown force densities times this vector, so it's bilinear. Bilinear, and here we have constraint. This is also just a product, and this is also new variables then, and how to rho A is the densities is even given, and the length is expressed in a quadratic constraint. So really we have only quadratic equations so far, but now we get a quadratic inequality as well. Sorry, a linear inequality as well, because for self-supporting we would have to write that this Wij is positive, non-negative. And this is simple. We just introduce another variable, new variable Uij, and we say this omega Wij is the square of Uij. So everything with quadratic or linear constraints. This is not enough. If you do just what I said to you so far, I will get very bad meshes. It will look terrible. But there is something else we need to consider. If we have a mesh, we may want that selected mesh polylines, like this one here, resemble the shape of a smooth curve. And to achieve this, one simple way is to require that a vertex is close to the center of the midpoint of the two neighboring vertices. So the midpoint of the two neighboring vertices here is Vi minus 1 plus Vi plus 1 divided by 2. This would be the midpoint, and this Vi we want to have close to it. However, this is not so nice since we are given a design surface. And if we have to go in a direction where my design surface has a high curvature, think of this. If you have here a high curvature, just also in the curve case it is clear. It will not be possible to bring this point close to the midpoint here. So this expression here, this fairness term, somehow tries to avoid high curvature, which is not feasible always. Yeah? So we do something different. Yesterday we talked about normal curvature and geodesic curvature. We would like not to have unnecessarily high geodesic curvature, but the normal curvature is given by our design surface and we shouldn't touch it. So what we will really make small here are these tangential components of this difference vector here. And without going into more detail, I just tell you this. And then we have an algorithm. for the following. We have these constraints, and now this is a different notation. X is a collection of all variables. So this is high dimensional, including the auxiliary variables. So everything is in this X. And then every constraint is at most quadratic. So it is of this form. So of course, the architects don't like it. X transpose times matrix times X is a quadratic term. Here's a linear term, and here the constant, right? And we do a linearization. So Taylor expansion means this expression taken at my current position of variables plus gradient times x minus the current position, and the higher order terms we go away. So this is linearization. And this is a linear equation now. So we have now linear constraints. However, we cannot solve this system of linear equations directly for various reasons. There is two main reasons why this is not possible. The first reason is this will be a design problem. So even if you try to solve this linear system, you should have infinitely many solutions. Yeah? Roughly, because we have this constraint variety is not just a point. Yeah? This is a higher dimensional manifold. So it will be underdetermined. But even worse, there will be maybe conflicting equations, because I told you that we, for example, for the planarity of a face, we do use all orthogonalities. Each edge orthogonal to a normal, and we get redundant constraints, and definitely through to some numerical imprecision, which is always around. These are theoretically conflicting equations. So this is bad. So what we need to do is we solve this system in a linear square, in a least square sense. So we make this residual, left-hand side minus right-hand side squared, as small as possible. But we add here, so this is this equation, these constraints, we add something with a certain weight, epsilon, that comes from the aesthetics, this polyline fairness. Yeah? This was also of this form. And then we have a third term, and this is depicted here. We have a vertex in a certain position, the next, and so on. We don't want that these vertices move too fast, like here, this is bad. Gradually move, because in an interactive design, this is important. So we take a third term that says, don't deviate too much for your previous part, a previous solution. And this we repeat here with decaying weights on this soft energy. So basically what we do, we have this constraint variety, we have, the mathematical viewpoint is this, we have a constraint variety and a point outside. Initially, we use this fairness quite a bit to get to the good region of the constraint variety, but if we are already in the good region, we don't care about this aesthetics anymore, because everything in this region will be aesthetic. Then we want to make sure that our constraints are satisfied to a high accuracy. And then, so the weight of this part goes away. Only this is kept because we need some regularization. And this, I think I have shown you. It is interesting observation. This is not that originally, after a few steps, this goes down quickly, this error, and then you already reach numerical accuracy. You can compare with other methods that do not use these quadratic constraints. And definitely, it is an observation in most of, actually in all of my programs which we wrote with this approach, that this quadratic formulation is really good. And this is an open problem for clever mathematicians. Why is this quadratic formulation so good? I do not know it. I have just a feeling. My feeling is a plausibility explanation. If I linearize a quadratic constraint, I basically throw away the quadratic terms, right? If I linearize a cubic equation, I throw away much more information. If I linearize something even more nonlinear, I throw away more information. This is not a strong argument, I know. But so I would really be happy if you come up with a good explanation of this phenomenon. I don't have it. So here are some results. I think we have seen this before. These are designs which are, for example, made by planar quartz, and they are in force equilibrium. This is an interesting thing. This is also self-supporting, and it is not a height field. So this has a quite complicated topology. It is interesting that you can build such a thing. It is self-supporting, and it's not just, you know, this standard cupola or this cylindrical shape or this dome-like shape. Is much more complicated. Here is the ground, so above the ground you hit the shell several times. It's interesting that it can stand just by compression. The video I have actually shown you, and I think it is it necessary to show again? No, you have seen it. So I think it works. Mathematically, just a remark also, one would think if we have a flat mesh, completely flat, and we are looking, say, for a planar quartz mesh, why don't we just start with a flat mesh? This should be a nice point on my constraint variety, and then I do some interaction to get another mesh. The reality is not so nice, because if we think of all polyhedral meshes of a given combinatorics, so say planar quartz meshes with a fixed combinatorics, then this constraint variety is composed of a linear space which belongs to the flat meshes, so where all vertices lie in a plane. Yeah, so same combinatorics, you have different, of course, realization as a flat mesh. This is this, I call it the trivial part. And then there is this interesting part, which is actually of the type I like, because I want something curved. And there is an intersection between this trivial part and the interesting part. If I start originally here, and I would just locally explore, so tangent space, I get nothing. I will always remain in this planar stuff. So I should give you an explanation of this part. And in this case, there is a nice explanation. Such a flat mesh lies on the interesting part of this constraint variety, if and only if you can find forces in the edges of this mesh which balance the mesh, so that it is in force equilibrium. So this is interesting that here in the good part, you already have this force equilibrium around. For actual manipulation with our system, it doesn't make so much problem, because you have seen this video. This guy pushes up a vertex, immediately removes it from the flat state, and somehow it works really well. What I also show you, you can also try to use other expressions in your target function, like area. You say you have some constraint on the overall area of the structure, volume. So here's such an example. We grow this structure, increase the volume, but the problem is that computing the volume is a global thing. So all variables will be involved, and then we don't have these sparse constraints like the planarity of faces, and then the thing is much slower. Another interesting thing for the engineers is we can even think of force fairness. Force fairness, I mean the following. This color coding is here the magnitude of force. And we do not want abrupt changes of forces in the bars. So here these are abrupt changes. You see I have blue, red, blue, and green, and so this is abrupt changes. We can do a similar thing as we did for the aesthetics of polylines for the forces, force densities, so adjacent forces are more equal, like here, so this is not so abrupt. Of course, the singularities are always a little bit of a trouble, and it is interesting to see that here, even if we apply a physical constraint, namely fairness of forces, we get, in fact, a positive geometric impact. It's not getting worse at all. It's getting geometrically maybe even better. Another thing, So far what I had shown you is cases where we have already prescribed the combinatorics of the mesh. Once again, the combinatorics means how things are put together. So the valence of vertices, how many quads are around the vertex, and so on. So we just move around the vertices, we change the geometry, but the combinatorics is fixed. So we can run a test case. We give a boundary, and we put different quad meshes inside this boundary with different combinatorics. And then we do an optimization, say, for flat quads. And then it turns out that the useful shapes here, and these are probably only these 3 here, maybe these also, these 4, look very similar. So this is somehow the combinatorics here has an influence, but fortunately it is not used. I say fortunately because sometimes, especially if this mesh is visible, if it is just beams and glass, for example, then the designer wants to have hands on this combinatorics. So it should not come out automatically. It's also something I want to say to all of you. I do not want to remove the architect from the scene, of course. We need the architect. I do not claim that we compute an optimal design, by no way. We want to provide tools so that architects and engineers can come up with designs that both meet the constraints on physics and manufacturing and also meet the design intent of the architect. So this is what we want to do. We can, this is a video which shows that we can, if you see it, this is unfortunately is not well seen. This is very sorry. Here you see the edges, hardly see the edges, but the guy does some manipulation of the combinatorics. But I can see this is worthless. It's not nicely visible. This we have done yesterday already. So actually, either we look at, no, we have just 5 minutes left. And in these 5 minutes, it's better if I take questions. So what are your questions you want to ask me? So 5 minutes, if I bring up another topic, it doesn't make any sense, right? No questions? Yeah?
One of your slides showed a structure and it said it's a self-support.
Yes.
Why?
Why? Because we optimized it so that you have this thrust network inside. So the mesh you have seen, so I think you mean this one maybe, huh? This one, yes. What you see here is a triangle mesh, and this triangle mesh is a thrust network. It means you can assign forces in these edges of the mesh, which everywhere are in balance with the loads. Yeah? And the loads, of course, you have to assume some kind of material here. I don't know with which weight it was computed. But it is proportional, of course, to the area here of such a face, the weight of a panel, yeah, and you have to put this into you have to distribute the entire mass into these vertices. And then here, the computation showed, this was the same tool as I have shown in the video previously. The computation gave this shape, and it is in force balance with compressive forces only within the limits you would like to apply for this type of material, and therefore it is self-supporting. Building it is another thing, because how do you build it? You cannot just start brick by brick and build it up, especially if you do not use mortar. You need a scaffolding. Yeah? You need a scaffolding, then you can put your bricks, and then you have to remove the scaffold, which will be more or less impossible with this type of shape. Yeah? And then it would stand. So actually only at the very end, when everything is complete, you remove this scaffolding, and then it will stand. This was also done for this design here, by Philipp Bloch. This is in front of a building in Zurich, at ETH Zurich in Switzerland. They had some scaffolding. They put up these bricks here, and then you remove the scaffolding, and then you see it stands. And what you also see, if you look into the web page of this guy, Philipp Bloch, ETH Zurich, he may still have these videos there where they they have to destroy this because the administration of the university didn't like that this structure is in front of the university. And then they came with big hammers and tried to bring it down, and it is surprisingly stiff. So you can put a lot of load, so they had a lot of weights put on it, and it still stands. And only if you do severe damage, of course, you know where you have to hit it. So if I have to bring down this structure, I do not bring it down here. I hit it here, right? Obviously, if you can manage to get this break, a large part will fall down. Not everything. Maybe this will still stand. Another question. Yeah, if this is not the case, then I thank you for your attention in these lectures. I hope you are not as tired as me after all these lectures. I also hope that you learned something. It is clear to me that you cannot teach an area of research within 5 lectures. This is clear. I think this was not the intention. The intention probably was to get you exposed to this type of work, and if you would like to understand this more closely, I think you have to study it in more detail. The presentations I have given away, and they will be uploaded, I have heard, so the presentations will be there. And I have also given you one of my course notes, which I recommend. This is a course notes on applied geometry, courses which I gave at KAUST, and they contain a lot of information on differential geometry, which is one of the basic areas which one needs here. Otherwise, I think, just say thank you and